Howdy y'all, it is I, the Diabolic vTutor, and we're back here to finish off the last time situation with the parabolas, graphing parabolas. So today we're going to be covering transforming your quadratics into vertex form. So let's get started. We have, if you recall from last time, with the parabolas, we have something already in vertex form. And by vertex form, it's going to look something like this. So we have a y is equal to, inside the parentheses, x minus 3, for example, squared, and then plus 1. So again, this is referred to as vertex form. If you have something else like this, for example, I gotta do the math. 9 times 2 is 18, 18 plus 1 is 19. So yeah, if you have a quadratic in that particular form, this is a quadratic as well, but this is referred to as standard form. Standard form because it's the most boring form that you can possibly get, and problems are typically written in this fashion right here. So when you're given something in standard form, you have to ask yourself, what am I doing with this particular parabola? Am I trying to graph it, or am I trying to solve for it? But in this situation, we're going to be attempting to graph the quadratic. So given this form, how do you transform it into this form to make it conducive for your graphing purposes? And it's not too bad. But first, we got to backtrack just a little bit, because there is something to understand with exponents, and specifically something called binomial expansions. But we're going to start off very, very easily. So if you have something like x plus 1 times x plus 1, just understand where the numbers come from. If you were to multiply factor number 1 to factor number 2, what will you get from the situation? So basically, if you sit there and you multiply it out, and then you learn possibly something multiplication algorithm called foiling, the FOIL method. It's the 4-letter F word. I don't particularly like FOIL. At least I don't like to call it foiling. I just like to call it distributive property, you know? So you have two things in here, and then you're trying to multiply it to two things in there. All you gotta do is be very methodical. But if you're following the FOIL algorithm, it's first to first. So you're multiplying item number 1 times item number 2, getting x squared. And then you go outside, it's the quote-unquote outer x from the medial times the outer 1 from the medial. So that's going to yield positive x, positive 1x. Oh. Alright. Hold on, let me take a quick drink. Alright, so that's the O represents for outside, and then you have the inside. Those are the terms closer to the medial, so you have to multiply 1 times this other x, getting positive 1x. And then lastly is last. What do you know? And then second term reading from left to right times second term reading left to right, so it's going to be plus this. You collect the like terms, thereby yielding x squared plus 1x is 2x, 2x's. This is a constant, so you leave it alone. So in conclusion, if you multiply those two factors, expand it out, you will get this as a return. Some people like to call it foiling. Again, I don't particularly care for the name. So therefore, if you have x plus 2, for example, and then you're multiplying it 2x plus 2, you could sit there and FOIL it out if you wish. So again, this one times this one, x squared, and then this one times this one is 2x. My suggestion, if you choose to do foiling, make sure you stack this correctly so the visually it'll be easier to add stuff up. So again, it's this one times this one yields here, and then this one times this one. I'm going to put it on the bottom like so, because these are like terms. Finally, last term times last term gets plus 4. So this is just some, putting it stacked like this is just for bookkeeping purposes. Not a particularly big deal if you're just working with quadratics. So summate straight down. I guess bookkeeping is more necessary when you do multiply non-binomials. So for example, if you have x plus 2, this is kind of a bit of a tangent. Well, let's say you have something like 2x squared minus 3x plus 5. So if you have something like this, obviously the FOIL ain't going to cut it, because foiling only works for 2 by 2s. And by 2 by 2s, I mean if you have something like x plus 2, there are 2 terms in here, and then you multiply it to 2 minus 3, 2 terms over there. So hence it is a 2 by 2 kind of this distribution. In fact, this is the same thing you will observe if you've taken any biology course where you learn about genetics, when you learn to do, what is this called? Punnett squares? It's a 2 by 2 Punnett square. Same thing here. You populate the x and the 2, and then you use those x minus 3, populate the box for the Punnett square style. So multiplying those two gets here, multiplying those two gets you this, those two gets you this, and then those two gets you this. So this is the Punnett square method. It's because Punnett squares, you're basically working with quadratics. It's just a 2 by 2 kind of multiplication scenario, but that's a tangent within a tangent. So this is still a tangent, of course. I'm just emphasizing the importance of bookkeeping and the irrelevancy of foiling. You're just basically distributing. Just be very methodical. So for example, we're doing a 2, 1, 2, by 3. So we're going to end up with 6 terms in total. It's going to be a nightmare, in my opinion, to keep track of if you just go linear motion. So rather than doing that, here's what I propose instead. You take this number, multiply to this, and then to this, and we're going to list them all out. Just for visual clarity, let's do blue. So this one times this one gets 2x cubed. That one to that one, it's negative 3x squared, and then lastly, and my suggestion is to cross things out. So you cross that one because you are done multiplying that one. And the next we picked up 2. This term here has to be multiplied to those 3 things. So first, and here's what I'm going to do. We know that it's going to yield a x squared component product, so we're going to put it right here. So positive 2 times 2x squared gives us positive 4x squared. And then this one times this one yields negative 3 times 2 is 6, so negative 6x. And then lastly, this one times this one, positive 10. We finished distributing that 2 to each of those 3's. Remember, this is a 2 by a 3 distribution, so we should end up with 6 terms right off the bat. We do have 6 terms. So when we're getting to summating those ones, the bookkeeping basically makes things very visually easy. So add down, add down, same thing. That's easy. And then you're done with the 3 by 3 distribution. But organization is pretty nice. But with quadratics, multiplying 2 by 2s, it's not terribly involved. So you can get away with sloppier bookkeeping skills. But it's just good to mention. Alright. So when we're doing the vertex form, I'm going to emphasize multiplying the same factor times the same factor. So x plus 3, for example, times x plus 3. So pay attention to where these numbers come from. Again, we have x squared, we have 3x, we have 3x, and then lastly we have plus 9. So if you summate those, this is coincidentally the same number. Gets us positive 6x, and then the 9 is here. So the middle term comes from the summation of this one and that one. So keep track of that. That's particularly important for the algorithm we're going to learn in a few moments. So if you have x minus 5, for example, and then times x minus 5, this is the exact same factor times itself, hence it's exponent squaring, right? So what do we get? We get the x squared there, we get the negative 5x, we get another negative 5x, and then lastly, is this a coincidence that they're the same? No, because these are the same. So summate those, you get negative 10x. Alright, set that aside. What if you have something goofy like this? If you have the 2x minus the 3, and then this is getting squared. Well, first let's just rewrite this. We can rewrite this as 2x minus 3. It's technically a waste of time, but it's just to illustrate a point. So what do we do again? Multiply those two. Product of those two. Product of those two. Is it a coincidence that these are the same thing? And then lastly, those two. So there we go. Yeah, there's a bit of the graph from last time. Sum those up. Oh, there you go. So let's make a few observations. So check this out. When you are doing an x plus 3 squared, you notice that it's a repeated number one just because this is an exponent of 2. We're repeating the same factor. So it's the same factor times itself. And because it's the same factor times itself, that's why this number here appears twice. But twice, if instead of just adding it, can't you just multiply? So 3 times 2 gets you a 6. Interesting. 3 squared gives you 9. Interesting. Check this one out. So expanded form is here. It's the same factor times itself. This 5 here appears once, and then this 5 here appears twice. And then times 2 gets you negative 10. And also, negative 5 squared yields positive 25. So I hope you're starting to see something. So when we have this one, for example, this is a little more complicated, but look what happens. This one multiplies here to get 1 negative 6. Again, this one times this one. This one times this one involves the exact same numbers, so also gives you negative 6. You have 2 of the same terms. Negative 6 times 2 is negative 12. And then finally, negative 3 times negative 3 gives you positive 9. 2x times 2x gives you x squared. So let's generalize this as an algorithm. So here we go. It's very simple. Very, very, very simple. But also kind of niche. So if we have something like x plus 11, for example, and you're trying to square this one, don't waste your time writing this out, unless you're practicing. So you can write it as x plus 11 times x plus 11 and do the foiling or whatever, the 4-letter F word. Please don't use that. You can instead use the algorithm. Now here's the algorithm. Okay. Square that. First square the first thing. Square that thing. And here is the quote-unquote shortcut. Take this number with the 1 in the front. There's always an invisible 1. Times 11. So that's 11x, and then times 2. That's 22x. And that's it. That's the algorithm. You just multiply first term times second term and then times 2 because it's a binomial expansion with exponent 2. So mechanically, why does it work? Well, we kind of already went over that, but let me show you in more detail. So expanding this out, we have x plus 11 times x plus 11. These two, it's pretty clear where those two come from. It just comes, this one comes from the product of those two. This one squared just comes from the product of itself. So where does this middle term come from? It's the summation of 11x and the exact same term, again, repeated twice. So 11x and 11x. So where does this 11x again come from? It comes from this one times this one. But this product involves the exact same number, so you're going to get 2 of these, hence the shortcut works. This one times this one gets you 1, times 2 gets you 2 of them, so 22x. So, practicing some. So therefore, if we have x minus 7, and this is getting squared, for example, you can expand this one very quickly. So square this. This one, first term times second term. Again, this is 1x times negative 7x gives you negative 7x, and then times 2. Gives you negative 14x, and then lastly, square those two. Positive results from negative squared. So it's positive 49. Well, then you are done very fast. Again, you can always use the 4-letter F word to multiply your binomial expansion of 2, but it's a waste of time. So why not use the algorithm if you can memorize it, right? So let's do another one. If you have 2x minus 3 parentheses squared, you don't have to sit there and expand this out. So first you square that. Use the algorithm, because this one will have to multiply to that one. You're going to get 2 of them, so times 2. So negative 3 times 2x gives us negative 6x, but then you times 2 because this term appears twice, thereby getting negative 12x. And then lastly, square those, positive 9. Well, then you're done. Distributive property algorithm for binomials of this nature. All right. So that's pretty nice. That's the distributive situation, but when you are doing quadratic problems, you actually want to go backwards. You don't want to distribute, you want to factorize. So this algorithm of, for example, 5x minus 3, if you square that again, multiply, multiply. So 5x times negative 3 times 2, so negative 30. Square those. So we are starting from this one for a typical quadratic situation where you need to graph it, and then you're trying to factorize it to become this form right here. Well, this is going forwards from a certain perspective, and now we're just going backwards from a certain perspective. So this one basically comes from well, you know what? Actually, we don't need to recognize perfect squares. Alright, so that's going forwards. So let's practice going the other way around. So if you have x squared plus 4x plus 4, how can we factorize this situation using what we just covered? Well, it involves a little bit of recognition. And the trick basically stems from this. If you take half of this and you square it, just the 4, not the x. So if you take half of this, it's going to be positive 2, and then if you square it, it is positive 4, which matches here, right? So once the set of conditions are satisfied, you could actually factor this one very quickly. It becomes x plus what? Plus 2. Quantity squared. And this might seem like another clunky algorithm that you have to memorize, but it's nice if you memorize it. You don't have to memorize it. Just pay attention to where the numbers have come from. So let me color code a few things. Let's color code this as blue, and then we'll color code this as magenta. So where are those numbers coming from again? So go forwards again. So if we have this one, let me do the expansion form first. So if you have x plus 2 times x plus 2, the summation of those two middle terms is going to get you 4x. And then the product of those two is going to give you 4, right? So keep track of that. Again, multiplying 2x times 2 gets you this. Squaring those two gets you that one. Same thing here. If you take half of this, it gets you here, but if you square that, it takes you here. Those are basically the same mechanics. So when you're checking to see if a particular quadratic is a perfect square quadratic, that means can you factor into this one? You run it through that criteria. If you take half, it's 2. If you square it, it's 4. So again, mechanically, that is 2. That is 2. Leads to here. If you square those two, it takes you here. Again, it's the exact same mechanic. If you memorize it, it's good. If you don't memorize it, well, things are just a lot slower. So let's recognize another one. So if you have something like x squared plus 6x plus 9, is this a perfect square quadratic? So half of 6, what is that? 3. If you square this one, do you produce this particular number? Yes. So this one is a perfect square quadratic. So when you factorize it, it's very easy. It's just x plus 3 squared. Because where this 3, what's the importance of this particular 3? It's this one. Because 3 times 2 gets you 6x in the middle, and then the 3 squared gets you the 9 in the end. So this takes you back right there. So again, that's the algorithm. So let's practice a few of these. Just to, I guess, solidify it. It's not super important because most of the time when you're graphing, most of your quadratics will not be perfect squares, but it certainly helps in some considerations. So is this a perfect square quadratic? Well, what's half of that? That's 5. Square that. Is this number? No, it's not. So we know this is not the perfect situation that we desire. So what would have been the perfect situation if this had been a 5 instead? So what's half of 10? 5. 5 squared? 25. So yes, this is a perfect square quadratic. So you can factorize this very quickly into x plus 5. There you go. Pretty nice. One more for good measure, maybe 2 more. And then you notice I'm giving very, very, very nice numbers. That's the usual situation. Until it's not, right? So is this a perfectly factorizable quadratic that ends up being a perfect square? Well, half of this is 4. 4 squared. Do you get this particular number? Yes. So mechanically, everything checks out. So therefore, you can factor this whole thing into x. Again, what's half of this? It is 4. Well, there you go. With great rapidity, right? Perfect. But in more practical terms, what do we even use that junk for? Well, at least in math. So here is a particular quadratic. We have x squared plus 4x plus 5. So right away, if you can run through the algorithm very quickly, half of this is 2. 2 squared is 4. This is not a 4. So unfortunately, it is not a perfect square quadratic. It's almost, right? Because half of this is 2. 2 squared is 4. If only this is a 4. But here's the thing. You can force it to be a 4. Okay? Here's how you do it. So all you have to do is take this, you don't like this particular 5 because it's stopping you from achieving your goals, so you break it up. Can't we do that? Isn't 4 plus 1 5? So with that little split, now you have a perfect square right there, do we not? Because what's half of 4? Half of 4 is 2. 2 squared is 4. Perfect. We can change this entire box thing and factorize it into x plus 2 squared. This leftover 1, just put it right there. And then you're done transforming your standard form for your parabola into now this vertex form, which makes it very conducive for graphing. Let's graph this junk as a review from last time. So we're going to take that, plant it right here. Now let's get to graphing this thing. Again, this is a review from last time. Where do we plant the vertex? How is the vertex changing from the parental position of 0, 0? It's going to be, how do you make this into 0? It's if x is -2, so we shift leftwards 2 spaces. So there we are. And then this is +1. All the y values get shifted upwards by 1 space. So that's our new vertex. We have a coefficient of 1, so it follows standard parabolic movement. So it's going to be from the vertex we've planted down here, up here, is going to be 1 to 1 movement, and then 2 to 2 squared, which is 4. I think I miscounted. 1, 2, 3, yeah. 4, and then 3 movements will be 9 movements. So right here. Yep. And then you connect the dots as smoothly as possible. Let me make sure the spacing is correct. 2 to 4, and then 3. What's 3 squared? It's 9. Takes you to 10. Yes. Okay. And then if you're particularly lazy like I am, just mirror it, because the parabola is perfectly symmetrical about here, the central axis that passes through the vertex. So 1 space, 1 space. 2 spaces, 2 spaces. From this location, 3 spaces, then 3 spaces. Okay? So exploit that to your advantage. You don't have to do it, but I prefer. Alright, and then you successfully graphed your parabola using vertex form. It's very strong. It works particularly well when you have even coefficients here and here. Well, actually right here. Generally, when you see a bunch of even coefficients, that's a prime candidate for graphing, setting up vertex form. Alright. Let's practice some more. Alright. Suppose you have y is equal to x squared plus 6. 6x. Already you're supposed to be running through. If you take half of this, it's 3. 3 squared is 9. So if I gave you a 9, that would have been perfect square quadratic. But I'm not going to give you a 9. I'm going to give you an 11 instead. Of course I would. Right? But that's okay. So even though this is not the perfect 9 that you were desiring, you can easily just break it up. So break that up into +9, which is what you want. Why do we want a 9? Because half 6 squared is 3 squared, which is 9. That's what you want to form the perfect situation. But you can't just willy-nilly change the 11 into a 9, because 11 is 9 plus 2. So once you have that, you take these ones together, and then you know this factorizes into x plus 3 following algorithm, and then the plus 2 remains on the outside. So we have finished converting it into vertex form. So the only thing left to do is to graph this junk. Let's do it. Very simple. So colorizing this as this kind of blue color. So again, find a 0? It's -3. So negative 3 spaces to the left and then 2 spaces upwards. Then we have coefficient out in front of 1, so it follows standard movement. So from this vertex, 1 to 1, 2 to 4, 3 to 9. That's kind of off. Yeah, it's like up here. Ooh, that's bad. Yeah, good enough. Alright, and then you just mirror it, so that's going to be ends up here, and then this one ends up being right there. Exploit the symmetry of the graph. So we're done. You should probably label a few things. This is going to be -3, comma +2. And that's it for the graph. Easy. But if you suspect I've been giving nice numbers, yes, I've been giving very nice numbers, right? Let's do another one. So suppose you have y is equal to x squared, and then this is minus 10x. So half of 10x, half of -10 is -5. -5 squared is 25. What if I didn't give you 25? What if I gave you 13? Instead, if only I had given you a 25, right? Because half of this is 5. 5 squared is 25. You desire a 25, but that is not a 25. But you just force it to be 25. But if you force it to be 25, you're changing the problem. So what do you need to do mathematically to quote-unquote change this back into a 13? Well, if you subtract 12. So this one in total, 25 minus 12, takes you back to 13. So perfect split. This one, you know, factorizes perfectly into x minus. So what's half of -10? It's -5. And that's following algorithm, and then on the outside is a -12. And then you're done. Pretty nice. Let's graph this junk. Let's move down here. Ooh, unfortunately the axes do not go down far enough. But that is okay. We'll just kind of fudge it. So this is down to -12. And figure out shifting rules. So our vertex will be relocated to +5 because +5 minus 5 is 0. So right here. And then we have a downward shift of the vertex 12 spaces. So from there all the way down to right here. It's a +1 coefficient again. So we know it follows standard movement. Not to sound like a broken record, 1 to 1, 2 to 4, 1, 2, 3, 4, whoops, 2 to 4, and then 3 to 9. So that's 7. Here. Hopefully that's correct. Well, if it's not, as long as you understand the idea, right? I wish I was a better artist. So we have a 1 to 1. Mirror this, or let's do some more work. So -1 to +1 movement, and then -2 to +4 movement, then -3 to +9 movement. So it's supposed to be like that. And then we are done, but make sure you label, otherwise you may be deducted points. So -5, comma, -12 is the vertex. Again, vertex is simply the lowest or highest point on your parabolic function if you graph it. Alrighty. Let's do another one. So let's make things a little more annoying at this point. So what if I gave you a number in the front like this disgusting 2 in front of your x squared, and then you are adding it to 20x, and then -1. So when you're dealing with this particular situation, unfortunately there's a 2 out in the front. We know, or at least I know, but just to point this out, when you do vertex form, sometimes you end up with a number out in the front. But the important thing is the x term inside this parenthetical has been factored, so it only has a coefficient of 1. Which basically I'm trying to tell you, if you see a number in front of your x squared, you need to factor out the number from your x terms. Otherwise, the mechanics will break down. So here's what you do for this particular problem. You slap on the old parentheses, and then you factor whatever you can from those two x terms only. Not from this one. This is the one that will fix everything else. But you got to deal with these ones first. So you slap on the parentheses and you factor out the 2, thereby making this coefficient just 1. This gets factored out. Factor of 2 gets brought out, so this is only 10x. Close parentheses, minus 1. So at this point, we haven't changed the actual components. We just rearrange things and rephrase things. So nothing has changed. We still ask ourselves the same question at this point. At this point, what do we need to do to make this a perfect square? Well, this situation is a little different from the prior situations. Number one, we have parentheticals, which makes things very annoying. And we have a loner number outside. So proceed as normal. I guess I'll just to show you. So in order to make this in the parenthetical a perfect square, follow the same rule as before. What is half of 10? It is 5. What is 5 squared? It is 25. And note what color I'm putting that in. So the reason why I'm putting it as a green 25 is because it was never part of your original problem, right? Do you see a 25 anywhere? Nowhere, right? So unfortunately, this has altered this entire equation, this entire function. And you don't want to change your entire function because now you're doing a different problem. So we need to offset this 25, right? So some people may be tempted to put minus 25, thinking that this negative 25 will negate this positive 25, which feels logical. But unfortunately, this is not only a 25, because this filthy 2 is out here. So the unfortunate reality is this one will be distributed to that one, generating positive 50. So your entire equation has been altered by plus 50. You don't want to do that. So you want to negate that 50 by subtracting itself. So minus 50. So that's minus 50. Again, how do we know that? Because this 25 was not here, but it's not just a 25. It's 25 times 2, which is 50. 50 was not part of the problem, so you need to negate it by subtracting 50. All right. So once you have that down, now we can just do cleanup. So we know exactly how this is going to factor out. What's half of 10? What's half of positive 10? It's positive 5. So x plus 5. That's just algorithm. And then negative 1 minus 50 is negative 51. And then you are done. So you successfully transform from this generic form into a vertex form. It's a little more complicated than before because the confounding coefficient in the front. Could we have skipped this portion? To a certain extent, yes. So if you're comfortable, if you feel like this is a different method than the first one I showed you, it kind of is. So let me talk about that. Well, let me delete these parts. It's kind of bothering me. All right. So we have this sort of situation, and let's not slap on the parentheses just yet. Let's see if we can avoid the whole situation altogether, right? I don't think we can avoid much of it, however. If you try to take half of this now and you square it, you're not going to get the right number, because again, this coefficient basically confounds everything. So to try to make this as nice as possible, no, I think no matter what, you have to slap on parentheses. So slap on those parentheses and factor out the 2 from the x terms only. Yeah, I think it just has to be this way. Half of this squared is 25. That's how you know this is a plus a 50, but you know, you need to cancel that by putting minus 50. Copy paste the minus 1. Yeah, so I would recommend doing it like that. The first method I showed you, let me show it again. Kind of circumvents the entire thing. So this is when the exponent with the coefficient is invisible 1. That makes your life so much easier. So for instance, if you have something like this is very easy because you can already ask yourself directly, half of this is 10. 10 squared is 100. This is not 100, but you can force this to be 100. But you're changing the problem, so you have to subtract it back to make it into 71. So minus 29. So when you do that, there aren't any multiplication shenanigans coefficients in the front, so this one is easily factorizable. And you just have a minus 29 out there. Alright, very simple. So we could split this. So again, the difficulty arises when you have an actual number in the front, like 3, for example, 3x squared. And then you have minus 6x and then plus 5. So what do we do in this particular situation? Make note, there's a 3 in the front, so that's going to be making things a little more difficult. So, you know what? No, you still got to show your work. So factor out the 3 from those two terms. Almost goofed up. So half of that is negative 1. Negative 1 squared is positive 1. So it's supposed to be plus 1 to make the perfect squared. But by adding this particular number there, we have altered the situation, because this is actually plus 3. So you need to negate that plus 3 by subtracting 3. Alright. So cleanup step, we know this one factors perfectly because we literally forced it to be that way. So half of negative 2 is negative 1. Combine like terms right out there. So we are finished. Y is equal to this entire thing. Let's get to graphing. So make note of where the vertex has been shifted to. How do you make this into 0? If x is positive 1, so we shift right 1 space, and then we shift y values upwards 2 spaces, so up to here. So our vertex ends up right here. That is 1, 2. And then we ask ourselves, well, how do we form the rest of the function, the graph of the function from this vertex? We have to follow the movement pattern of this 3 coefficient out in the front. So let me colorize this as red. So instead of being a 1-to-1 movement with the parental function, we have a modification of times 3. So it's going to be a 1-to-1 times 3 movement. So up to here. And then the 2 movement, instead of being 2 to 4, because 2 squared is 4, we instead have 2 to 4 times 3 modifications. So up here and up here. So somewhere way up there. And connecting the dots as smoothly as possible. Here. That's bad. Okay, good enough. Bad, but good enough. Same thing with the left-hand side of the function. It's a 1 to positive 3 movement because of this 3 coefficient. And then it's going to be a 2 to 4 times 3 to 12 movement. So 2 to 12 movement is way up here. Connect those as smoothly as possible. And we're pretty much finished with the function. If you're feeling particularly paranoid, you could always test numbers. So this is 0, comma 5. So if this function is good, then if we plug this in, it better work. So if we plug in 0, 0 minus 1 is negative 1, squared is positive 1, positive 1 times 3 is 3, 3 plus 2 is 5, checks out, this point is properly predicted, so the graph should be good, and then the function should be good. It's not 100% proof, but it gives us great confidence that it's good. Okay. I do want to explain a little bit more about something. Going back to shortcut methods, so if you have something like y is equal to x squared minus 4x plus 8, you can use the exact same method as the one with the coefficient in the front. So here's what I mean. You slap on the old parentheses and then you check, do we need to factor anything from this x squared? No, we don't. So complete the square at this point. So copy paste that. What is half of negative 4? It's negative 2. What's negative 2 squared? It's positive 4. This positive 4 was never part of the situation, right? So at this stage, you could actually split the 8 if you wish. So 8 minus the 4 will get you the plus 4. So that's the shortcut that I would use to avoid this, writing this out. But if you wish, you can always do it like this. So copy paste the plus 8. And then you manually negate the plus 4. Is it only plus 4? Yes, the coefficient is only 1. So you negate this only plus 4 by subtracting 4. Cleanup step, we know this one factorizes following algorithm, negative 2. Squaring. Combine like terms, so it's going to be plus 4. So as you see, same method if you're using the long form. If you hate memorizing multiple stuff, then I just advise always slap on the parentheses. Factor if needed, but if you don't factor anything, understand that there's still a 1 outside. So 1 times 4, you negate by subtracting only 1 4. So to contrast that, y is equal to 2x squared plus 4x minus 8, for example. So x terms are here, slap on the old parentheses only around the x terms, not around this one. Is there a number in front of the x squared that's not 1? Yes, that's a 2. So you got to factor 2 from those two. Becomes 2 times. At this point, we haven't altered the scenario. We just rephrased a few things. So complete the square for this one. So half of that squared is positive 1. I'll put that in green, because that's not part of our original function. But it's not just a plus 1. It's a plus 1 times 2. So to negate that, we have to subtract 2 times 1. So minus 2. This 8 here, copy paste. Follow algorithm. Everything else, copy paste, simplify. There we are. We have the vertex form. All you need to do is graph that now. Same methodologies as before. Find the vertex. How do you produce 0? On the inside, if x is equal to negative 1. So we have a negative shift. Shift 1 space to the left. And then we shift 10 spaces downwards. Way down here. What's the coefficient in the front? It's a 2 coefficient in the front, so all our movements get multiplied by 2. So 1 to 2 movement And then 2 to 4 times 2, which is 8. It's up here. That's typically good enough. But if you want to be robust, 3 to 9 times 2, which is 18. So we have to move 18 spaces upwards. That's 10, 15, 18. Again, not totally necessary, but you can do it. Alrighty. I'm particularly lazy, so I'm just going to mirror the points. So this one mirrors to here, this one mirrors to there. This one mirrors to there. So again, I counted 3 spaces to get to the line of symmetry, and then 3 spaces to the same height point right here. We should probably label that. So that's -1, comma, -10. And there you go. The graph is successful, but final situation, let's just check for posterity's sake. So this point right here is +2, +8. Ooh, that's a bad color. Let's check it out though. So 2 plus 1 is 3, 3 squared is 9, 9 times 2 is 18, 18 minus 10 is 8. So this one seems legit. So our graph is probably good, and we're good to go. I guess we'll do a negative scenario, because all we have are positive slopes. Positive quadratics. So occasionally someone might be trying to juke you out. They're trying to troll you or whatever. They're going to give you a negative leading term. So here's how we do it. Or here's how they would do it. Plus 8x, that's not conventional, and then minus 2x squared. Let's change this up just a little bit to 11. And you know what, let's change this to, let me change the positions. So you might see a problem written like this. Things are deliberately out of order. You know, for the visual attack on students. They want to, whoever designed the problem just wants to throw you off a little bit, but don't be intimidated. Just understand that things have been moved around. So this does not follow standard form order. This is x squared on the back for some reason, and by back I mean from left to right, from a Western reading style convention. So this is in the back, so just manually move it up to the front. So take that again. If you as long as you keep the sign attached to the right hand term, you can take this one and treat it as a plus and move it wherever you wish. So it's going to be this entire thing plus minus 2x squared. This one technically has an invisible plus. And this 11, nothing special happened to it. So here we go. We now have a more standardized looking form. Unfortunately, well, not unfortunately, but just take a quick survey. We have x squared, we have x power 1, and then we have x power 0. Everything is in order. There is an unfortunate coefficient right there. So slap on the old parentheses and factor out the -2 of those two terms. Watch out for sign flips. +8 divided by -2 is -4. You know, because quick check, -2 times -4 gives us +8. Checks out. Nothing has been altered from our equation. We just rearranged a few things. But to save work, I'm just going to move this one over. So if you wish, you could write it exactly like this. So what do we need to add right here to complete the square? That's half of -4 is -2. -2 squared is +4. This +4 was never part of the original situation, so we have to negate it. But remember, it's not just -4. Because this one only negates this one. This is actually twice that many. So what is -2 times +4? So in actuality, we've altered this function by subtracting 8. So to negate the subtraction of 8, it's not minus anymore, it's plus. So that's not a minus 4. That's a plus 8. So again, this plus 8 will negate the negative 2 times the positive 4. This negative 8 is thereby cancelled with that one. Okay, leaving with the 11 that we had in the original, so that's good to go. So from here on out, it's just clean up, copy paste everything correctly. This one factorizes what's half of negative 4, that's negative 2. Summate. We are good to go. How do we graph this? Well, unfortunately, the 19 goes off the page, right? Yeah. And in rather unfortunate circumstances, the 19 goes off the page, so we will have to manually move this up. Alright, well, perks of the digital medium, right? Want to take this? Copy paste, perfect. So now it goes up to 20 right here. This is 15. We need a 19. Oh my goodness. All right. So here we go. Same procedures as always. How do you make 0? It's positive 2. So let's shift rightwards 2 spaces. Shift 19 spaces upwards. So way up here. How are we moving away from this particular vertex? It's been altered by negative 2. So instead of moving 1 to 1 from our vertex, it's going to be 1 to negative 2 movement. Instead of being 2 to positive 4 movement away from our vertex, it's going to be 2 to negative 8. But let me make sure I'm lining this up correctly. Negative 8. Okay. So negative 8 will take us to 11. So we're down here. And then lastly, let's actually graph something on the graph. So it's going to be 3 to 9, but then there'll be 9 times negative 2, which is negative 18, which takes us down to positive 2. Right there. So connecting this as smoothly as possible. There it is. Axis of symmetry is at positive 2, so let me grab the other point. So this is 3. So that's 3 to the right takes us right here, but 3 to the left will take us right there. Because again, exploiting the symmetry of the parabolic function. And the rest of this is just kind of artsy. Well, that's not a real point. But I'll try to put it. Yeah. Good enough. Although this one is going to be like this. If you want more robustness in your function graph, make sure you mirror the points correctly. Okay, so that's basically it. If you're feeling, again, if you ever feel particularly paranoid and you have time to spare, just test the point. This is going to be we counted points, we counted spaces to get to this point. So we predict -1, 2. So that should work if we plug it into here. So if we plug in -1, we're supposed to get 2. So that's -3 squared is 9. 9. Ooh, that's actually off. Did I miscount spaces? See, this is why it's sometimes a good idea to check. So if we plug in 1, this becomes -3. -3 squared is 9. And then 9 times -2 is -18, which gives us +1. So I believe I miscounted spaces. So, whoops. Let's fix that real quick. Such is the problem with graphing with crummy graphs. So here we go. It's supposed to be +1 right here. So this one, therefore, should be here. Well, I guess now we got to double check that one as well. And if it works, it's going to be good enough. So this is going to be +5, 1. This is a mess now. Whoops. I should have undid all that nonsense. Let's just write it again. So again, we're curious if this is going to be, if this graph is good, assuming the assumption is this is correct, which may not be true, right? All right, plug in 5. That's going to be 3. 3 squared is 9. 9 times negative 2 is negative 18. Plus this one is positive 1. So it seems legit. So I'm going to trust this one for now. And we are good to go. I think that's it for now. I'll probably stream again, covering factoring quadratics in general. So this is when you're given very nice numbers. Sometimes you might be given obnoxious numbers. And let me just show you, for example. So if you have y is equal to 2x plus 14, 2x squared plus 14x minus 7, for example, then whatever I taught you, whatever we've gone over so far, still is applicable, but the numbers are just more disgusting. So this one, slap on parentheses and factor out the 2. And lo and behold, here's where things become nasty. You have a half of 14 is 7. It's disgusting. I know. What's half of 7? It's going to be 7 over 2. What's 7 over 2 squared? It's 49 over 4. Technically, you don't have to write this step, but it's useful to figure out how do you correct the number on the outside. So technically, again, you could opt not to write that if you're comfortable with shortcuts, and you just jump straight to the factored form, which will be plus 7 over 2. So you kind of avoid having to stare directly at it, but unfortunately it doesn't help some people with generating the correcting term. So what I mean is you still need to account for this 2 times positive 49 over 4, right? But luckily these numbers kind of work out. So it becomes 49 over 2 positive, which was not part of our original problem. So you need to negate this one by subtracting itself. So that's gone. So when you start to clean everything up, again, what's half of 7? It's 7 over 2. So we kind of ignore this after we correct for it. And then minus this nastiness, this is just 14 over 2. So combine those, it becomes negative 63 over 2. So can we graph this one using our typical conventions? Yes, we technically can. It's just really bad because the axes don't accommodate these small increments. But I could show you, right? So where do we plant the vertex? So unfortunately, I'm going to change this to mixed numbers to make it slightly easier to look at for me. So that becomes 3.5, and then this one is a whopping 20. Wait, what am I saying? 31.5. Right? 62 plus 1 is 63. Yes, that's correct. So graphing it is really, really annoying. So the x movement, we need to, how do you make this into 0? If it's negative 3.5. So negative 3.5. That's our x movement. And you notice I'm using the half hash mark, so it's here. And then we have to move downwards 31.5 spaces. So pretend, okay, just for a moment, please, that this is negative. No, I feel bad doing that. I shouldn't. So this is, no, I have to. I'm sorry. I just have to do it. So we have to pretend, for example, this is negative 31. So we have to go downwards all the way to 31, to negative 31.5. So it's a little bit past here. So it's going to be like, this is the full one, you're half, like right here. Yeah. We could still do counting space movements. So this is a 2 coefficient. So when we move one space away, you just have to move to a half space, which is right here. So that's one full movement to the right. But then we're going to move one space upwards times 2. So you end up in this half space. So not my favorite thing to do, but it's perfectly doable. And then you would move 1, 2 spaces, and then 4 times 2, which is 8 spaces upwards. So half a space, well, half square is 1, 2, 3, 4, 5, 6, 7, 8. So counting spaces isn't totally superior, but with nice numbers, it's very fast. There it is, just mirror the points. I can pretend this is a 31. It's not really 31, but what can I do? Here we are. Here. Oh, goodness. There we go. We are finished doing the graph. I don't want to test this because these numbers are really, really bad. Oh, I know the trick. You know the visual trick for graphs? If they are too long, all you have to do is truncate your graph. And here's how you do it. It's kind of goofy. Okay. So I'm going to do this and obliterate this entire section. And then I'm going to put like a little cutoff, this little squiggly symbol. So that means that it's been truncated. It's been graphically truncated because I can't draw this one very well perfectly. So I'm gonna have to cheat by truncating the graph. Is that a dirty thing to do? Yes, it kind of is sometimes because you can visually trick people. That's okay. So again, this has been visually cut, and this has been visually cut. But we do what we can for the sake of convenience, at least. But I think that's about it for this particular stream. I'm going to probably stream a little later. Maybe I'll cover... Oh, actually, the original plan was to cover factoring again. So factoring quadratics, maybe factoring polynomials in general. But that one is a little bit more involved. It's going to involve kind of many algorithms, unfortunately, such as Descartes' rule of signs, which is itself really annoying to deal with, and then the synthetic division multiple times, and then synthetic division tests, which is really annoying, sign change, which is Descartes' rule of sign, and then maybe intermediate value theorem, which is also annoying, but maybe. Okay. That is it for now. I will see you perhaps another time. Signing off, because I need to eat food.